Right, okay. So it starts. We try to simulate the natural wind. Every university in Canada has a wind tunnel, at least one, maybe two or three. But this is special. Why is this special? Because the other universities have, for purpose of aerodynamics, testing plane wings and so on. So basically they deal with the so-called aeronautical aerodynamics. That's the classical way. What we're doing here is something very, very different, because what we do here is we deal with the atmospheric boundary layer, because we're interested in the interaction between wind and things on the surface of the Earth that everybody understands, whether these are buildings, buses, trains, people, whatever they are near the surface of the Earth. And that's where things are much, much more difficult here to study, because the wind interacts in various ways with the various obstacles that we have here. So what do we do here? So we simulate the natural wind. The whole idea here is that when the wind blows towards us, and when the wind reaches this place here, which is a turntable, and on this turntable we put models of buildings at a particular scale. Scale is important. Geometric scale, time scale, there are all sorts of scales here. Because what we're doing is we try to kind of, without changing the basic characteristics, generate the wind properties. So this is not just the air that you get at home when you put your fan on because it's warm in the summer or whatever, just let's put the fan on. This is not the same. This is the real wind. Real wind means that it has the same kind of characteristics with the natural wind, but scaled down. Let's look into the boundary layer. Let's say there is a profile of the wind. The wind is very low near the ground because of friction. And then as you go up, of course, you go up on the mountain and so on, you have higher and higher and higher winds. So this is a characteristic of the wind, change of the velocity with height. It increases with height. We have the same characteristic here, but at a scale. In other words, it's about 300, 400 times smaller if I want to test a building. If I want to make the building 300 or 400 times smaller, for instance, then of course there is similarity. And whatever I measure on this building is going to be what I'll be measuring outside in the field. And that makes the trick. That's what makes the test meaningful. There are time scales. Now, time scales has to do with the fluctuations of the wind, the vortices, the eddies, the ones that you can see very easily in the water when you go into your tub or whatever, but you don't see them in the air unless there is snow. And then the snow visualizes things, and then you can see some snow particles going all over the place and so on. Now, this all over the place has to be represented here. So this one here represents really an open terrain, something like Saskatchewan, prairie, whatever, or sea, or lake, or whatever it is. But when we have a real situation, we want to test a real building, then of course we put the reals around it at a scale. We put them on a turntable so that we can rotate from 0 to 106 degrees, which represents different wind directions, because I cannot change the wind tunnel. So basically I change the model, that's the trick. Now, there are two types of applications. Structural wind engineering, we call it, and environmental wind engineering. Structural wind engineering is basically the interaction of the wind and the structure. Pressures, forces, overall the building will move, will not move, and so on. It's exactly the same interaction that you have when you go to swim and there is long waves and so on, and of course the waves push around and so on. It's the same thing, okay? So just to give you an example, because this is a structural wind engineering project, what you see here is a building, a generic building. It has been made in such a way because we measure pressure now on a canopy. Because canopies are very prone to wind, so we have to design for them. We have to know what loads are there. And it's very tricky because you have loads on the upper surface, you have loads on the lower surface, you have to combine them together. You may have a canopy at this height, at another height, and so on. So the model accommodates that. They can put the canopies at various heights and then do the measurement. And they come up with results, millions of numbers, of course. But these are all pressures, forces on the building. So that's what structural wind engineering is. It's just a structural application. We want to know the structural load so that we do a lot of work for the building codes and regulations and so on to tell people what to design for. That's the main application that we do. Okay? Now, environmental wind engineering, we define it by exclusion. Any other interaction which is not structural, that you know what it is, it's called environmental. That covers everything. Pedestrian level winds, the winds that they take your umbrella and so on. Ventilation, natural ventilation, sustainability issues and so on. Wind-driven rain, how the rain kind of goes and affects the envelope and so on. Wind energy, which right now is very kind of timely because we have this over here. We do a lot of work on this so-called urban wind energy, which is wind energy in the cities. What we're trying to do here is integrate the wind turbine and the building. But of course, this is much more difficult because the wind is not really that good in the cities, okay? Because you have a lot of turbulence, you have various frequent kind of wind directions. So we're trying to optimize things to make them better. So this is the environmental wind engineering, everything else. The reason that we have relatively high wind, not very low wind, is simply because the instruments perform better. Through simulation, we can simulate any wind that we want here.